Today I am going to talk about the binary phase diagram. Why do we care about the binary phase diagram? Solid mixtures have many applications in life. The properties of certain ratio mixture of two different metals can be more helpful in life than the pure substance. An example for that is steel, which is the solid mixture of iron and chromium, magnesium, or nickel depends on the purpose of the steel. We use steel for crafting daily supplies and structural building materials. Since solid mixtures serve an important role in our life, the study of solid mixture is necessary. We can study the solid mixture using the binary phase diagram. Before the binary phase diagram, we should know about the Gibbs phase rule. The Gibbs phase rule is pretty simple. It's just F equals C minus P plus 2. F is the numbers of degree of freedom, C is the number of components chemically, and P is the number of phases, and 2 is just there. So now we know the Gibbs phase rule. We should know how to use it in the phase diagram. The phase diagram I chose is the single component phase diagram. The reason why I chose this phase diagram because it's easier to read than the binary phase diagram and tertiary phase diagram, and it's just the most common known phase diagram. So in this diagram there are three phases: solid, liquid, and gas, and I label the numbers of degree of freedom in three different places using different color. The purple F is at where solid at, so F equals 2 because there is only one phase, so F equals 1 minus 1 plus 2 equals 2. At the blue F is where the solid and gas intersect, so there are two phases in total. So the blue F is 1 minus 2 plus 2 equals 1. At the green F is where the three phases intersect. So in total there are three phases. So the green F is 1 minus 3 plus 2 equals 0. So what really happened in the binary phase system when the temperature changes? The system I chose for this example is the liquid-solid binary phase. So in the beginning is two immiscible liquid A and liquid B, and they are two different liquids, so they have different freezing point and melting point. So in the beginning they are happily floating around. So what happens when the temperature changes and drops? The liquid B with the higher freezing point change into a solid first, and the other one with the lower freezing points remains liquid. So what happens when the temperature drops again? Both of them became solid. So before we get to the actual phase diagram, an important concept to know is the eutectic point. Eutectic point is the point in the phase diagram indicating the chemical composition and temperature corresponding to the lowest melting point of the mixture of compounds. So this is the actual solid-liquid system binary phase diagram. In this graph, we can see that it's measured in temperature and it depends on the mole fraction of B. So at where mole fraction of B equals 0 is where the pure substance of A at, and at the mole fraction of B equals 1 is where the pure substance of B at. So in this case, outside the boundary is the liquid phase. So at point B, where at the boundary is the liquid phase where it's about to go into two phases. The other phase is the solid, but it's still one phase. So in the down here in point C is where actually there's two phase area, so it's solid and liquid together, just like this one, like solid and liquid together. At point A is where the eutectic point at. So in this graph, we can see that it's the lowest point here, so it is the lowest melting point in the mixture, and eutectic point at the eutectic point and the area below it is where the both components are solid. Okay, thank you for watching.